Okay. Okay. Welcome everyone. Happy Tuesday. So I want to give an introduction to Amy Lau. She is an undergraduate student in my lab at UC Riverside. Just to give a little bit of background, so she's a senior now, but she joined my lab at the beginning, a little less than a year ago, at the beginning of summer. So with no background in mass spectrometry. So I'm very proud that she took all these things this far. But she's just a little bit more background. So she's senior in data science at UC Riverside, and will be graduating in a few short weeks. So I think it's a big accomplishment. Additionally, if any of you are in the hiring mood, she's excellent. So definitely reach out. But I want to introduce what she's been working on. She can talk a little bit about it, but it's called multiple mass spectral alignment. And it's a new way, I think, and a piece of software as well to enable a new way to look at molecular networks and tandem mass spectrometry at a little bigger scale than we're all used to. So I won't take any of our thunder, but the floor is yours, Amy.
Good morning, I'm Amy, and as Ming already mentioned, I'll be presenting on how we can improve the interpretability of molecular networks using a tool we developed called MMSA, which stands for Multiple Mass Spectral Alignment. So I'll start with a bit of background on molecular networking and then talk about the motivation for creating this tool, the challenges of aligning MS spectra, how we approach the problem, and then I'll wrap up with a quick demo of the tool. So molecular networking is a widely used approach in metabolomics that groups MS spectra based on their similarity. And these networks form molecular families, which helps us visualize structural relationships between molecules. In practice, this allows researchers to identify known metabolites and prioritize novel ones for isolation. So while molecular networks tell us which spectra are related, they don't really tell us why. That is, they don't explain what shared fragmentation patterns are driving those relationships. So from a scientific perspective, being able to determine which fragments are shared across spectra helps with metabolite annotation and can facilitate the structural annotation and discovery of novel metabolites. However, existing tools don't fully support this level of interpretation as of right now. They're limited in how they tell us, they let us explore fragmentation patterns across entire molecular families. Most existing platforms right now only support pairwise comparisons of spectra, which limits our ability to see fragmentation patterns at the molecular family level. And of course, they don't really offer a way to visualize shared fragmentation patterns across all spectra in a single component. So to address this, we have developed Multiple Mass Spectral Alignment Tool, MMSA, and it's an interactive web-based platform available on GNPS2 that takes a molecular family and aligns all MS spectra within it. The tool identifies consensus peaks, which represent fragments shared across multiple spectra, and then visualizes them to help interpret the relationships. Users can explore alignments, filter by intensity, and click on peaks to see where they appear across all spectra. So this is just an example output. You can see that we have all the spectra and then the peaks for each one. And here we have the top 3 peak sets. This is just the initial visualization at the beginning when you first load it in. We have the top 3 largest peak sets in red, green, and blue. Red being the largest, followed by green, then blue. And I'll talk a little bit more about it when I do the demo, but this is just to get a quick preview of what we'll be seeing. Now that we know what the MMSA tool does and how it looks, let's talk about how it actually works. But before getting into the algorithm, it's important to understand what makes aligning MS spectra challenging in the first place. So given a molecular network with several MS spectra, we need to align spectra to find peak sets across spectra. Our goal is to find peak sets, that is, a group of peaks from different spectra that are likely derived from the same chemical fragment. However, we have 2 main challenges to consider: mass shifts and peak intensity variation. Molecules might differ by small modifications, which can cause fragment peaks to shift slightly in M/Z. So we need to align not just the exact M/Z matches, but also shifted ones. And for peak intensities, the same fragment might appear as a strong peak in one spectrum and then as a weak peak in another. And since intensity is used in alignment scoring, lower intensity peaks might contribute less to the score, which can cause them to be excluded from peak sets, even if they represent structurally meaningful fragments. So because peak intensities vary and slight mass shifts occur, finding all matching peak sets across many spectra quickly becomes computationally expensive and complex. But to make the problem computationally efficient, we use a greedy algorithm approach. And this determines the alignment order by connecting the most similar spectra first based on their pairwise cosine similarity. And then within each spectrum pair, we identify all possible peak matches within a mass tolerance. And then we score these matches by the product of their intensities to prioritize strong fragment signals. And then we finally greedily select peak matches that maximize the alignment score while avoiding any conflicting assignments. While this greedy approach is efficient, it can sometimes lead to suboptimal peak selections. And since we're using a greedy strategy, MMSA can sometimes choose shifted peaks over exact match peaks, especially when they're more intense. So here we have an example. The set is the blue and the red, and we can see that it has chosen the shifted peaks in blue over this exact match peak in green. So the actual set is these blue and red peaks, but it does that to maximize the size of the set. So it chooses not to include this green one, even though visually we can see that the green one is obviously an exact match. Okay, with all that being said, we can finally see what it does and how it works. So typically, I think Ming is more familiar with how you can access it on GNPS2, but I just have a link directly to the page.
Let me put one in the chat here as well, just
Yeah.
so everybody can follow along. All right, go ahead. I think I put it in the chat. Go ahead, Amy.
Okay, great. So when you get to this initial page, we have two main options of how you can input the data in order to align the spectra. So the first option is to input your task ID and component number. And we just have like default ones right now. So if you want to follow along, you don't need to input anything at all. And all you have to do is process and save the JSON file, and that will grab all the sets, make the alignments, and then we can view them. But before we do that, let's talk about the other option, which is USI input. And you basically just grab all the USI of the molecular network that you want to visualize the alignment for and put them in line by line, and also click process and save JSON. So let's look at it. So this is the visualization page. It should look like this if you're following along. Let's talk about the visualization first. So we have all the spectra right here and their scan number and precursor M over Z values here. And our initial output, like I said earlier, is the top three largest sets in red, green, and blue. And then if you want to visualize a certain set, like a specific set, you can click on peaks, and then it will show which peaks are part of that set based on our algorithm. Now, it's not, of course, like I mentioned earlier, it's suboptimal, so it's not 100% correct, but you can explore any peaks you want, and it will show all the ones in red, all the ones in that peak
just want
set
to
in
be,
red.
as a computer science feedback, when Amy says suboptimal, that is a term of art in computer science. Now, whether that has a strict alignment and bearing in like the truth of this peak being the same like fragmentation point in those molecules, that's a little different. So just as a clarification. So
Yeah, so like when we compared it with actual like manually determined fragmentation, sometimes it would be missing one of the peaks that our algorithm determines as part of the peak set. If you click on a peak and it's not part of a peak set, let me see if this one, and it's just like it's in its own thing, not part of any fragmentation, it will just appear highlighted in red just by itself, standalone. And we have at the top options to customize your visualization. So if you want to customize the order, you would select custom order, and then maybe you want to see scan number 999 first and this one last, and it will automatically output like that. Another option to do that is right here when you select the spectra. You can view only a few of them if you want, and it will automatically change the visualization to just those that you have selected in the checkboxes. You can also just sort by ascending or descending order. See if we do ascending, and this is ascending based on their precursor M over Z values. Oops, let me recheck all of these. And if you want to zoom in a little more on the visualization, you can also adjust the x-axis lower and upper limits. Here we have a pretty good visualization of it, but I'll just zoom in for example. One thing to note is that if you do zoom in, the peaks will become larger and fatter, so it's not a very pretty visualization, but this is useful for if we have a bunch of peaks. Let me show you this one. So this one, we have a lot and we want to like zoom in a little more to see closely. We can adjust the lower axis limit to 200 and kind of zoom in a bit more so we can see the peaks more clearly. And then on top of customizations, we have the info on the peak sets. So first of all, we have set info. These are all the peak sets and just an arbitrary number that they've been assigned to, but it gives you information on their set size as well as the percentage of peaks in this set that rank among the top 10 intensities of their spectra listed right here. So what that means is if it has a high percent, it means that our peak set has, more of the important peaks in that spectrum versus like if it has a lower percent like this one, it probably doesn't have that many important peaks from the spectrum. But that just means that it's chosen like smaller peaks versus larger intensity peaks. Oh, and you can also select, like, let's say you want to see the set that has set size 7, this one, you can select it and it will automatically show you the set. If you're interested in like, oh, what's the one with only two peaks inside, you can select that one and it will automatically show you down here. And then on top of that, we also have the set info. So any set that you've clicked on, let's say this one, it will automatically update the set info so you can see which scan numbers are included, the peak index of which peaks are in this set, and then their information as well. And that's a short demo of like how you use this. If you have any questions, please ask away.
So let me ask you this, Amy. For the USI input, why would you want to use the USI input as opposed to like a GMPS2 task ID and a component number?
Yeah, so opposed to a component number, we have a bunch of already like set molecular networking families. But if you do want to only like customize your own like molecular network, you can grab their USIs and make your own basically.
Okay, cool. Yeah, so I think maybe just to rephrase that, sometimes the molecular networks aren't perfect, or you don't even want to run into molecular networks. Say, screw molecular networking. I want to take my own MSMS spectra from my own samples, and I want to look at this global alignment or multiple alignment together. So it maybe gives us a little more flexibility.
Yeah.
But cool. Any questions? Any other, high level questions from the audience? So just one small point is all these things are tightly integrated on the GMPS2 side. So we have it deployed on all our servers, and it'll work with feature-based molecular networking, classical molecular networking, and any USI that we can resolve. So this is kind of nicely integrated together. So Amy put a lot of work into that. And it's mostly on my plate now. We've got to get the manuscript submitted. So hopefully you'll see that sometime out very soon. But yeah, I think, yeah.
Maybe one kind of like very practical question. If I have a feature-based molecular network and now I want to further interrogate like one of my subnetworks, what is like practically like the best way to get like the USIs into that input field from the subnetwork?
Oh man, it's not great. It's not great. There is, I believe, you can download a table that'll tell you like the scan numbers, but then you have to construct this USI yourself.
But that would
You
not
can,
be, so you just need to replace the last number in the string.
that's correct. That's correct. That's correct. So you'd have, it's not the most straightforward thing, but it's also not super hard. But if they already form a family in the feature-based molecular networking, you can just put that in here. Oh, actually, there is a utility that you give the task and a component, and it gives you all the USIs. I just don't even know where that is anymore. But I built it. It's deployed somewhere on the internet, and it did do this for this exact reason because somebody asked me this question.
All right. Thank you.
So maybe I'll put a little, I'll find it. We'll put a little link. It's like, want to get a USI for a component? Here is the utility for it. There was a question from the audience. Let me see. Here's a question for you, Amy. All right, so we'll answer it together. Does this work for data from all mass spectrometers?
It's just the data that's like on GNPS2, I believe, because I'm pulling data from GNPS2 itself when we're generating the alignment and the peak sets.
Right. So definitely it has to be there. I think some of what this question is asking, again, don't expect you to know this as kind of only working on this for like 9 months, but there is, it should work for Orbitrap, QTOF, ion trap instruments, as long as you have tandem mass spec for it. So here, Amy is showing pulling from, on the USI side, clustered consensus spectra. It can also source it from raw data from the original files, again, if you choose for that flexibility. Okay, so Miranda asks, can you use it on MS, or is it only appropriate for MSMS? Tandem mass spec.
I
What do you
believe
think?
MSMS because of the fragmentation that we need for the analyzation. Yes.
Right. So molecular networking only works on MSMS. So MS1, you probably could put it in there. So Miranda, if you wanted to put MS1 in there, you could. I don't expect it to actually be meaningful given the algorithm design that we did. But if it's interesting, try it and let us know. But I just don't expect it to be great.
Oh, I think there's another question in the chat about,
yes, try.
Yeah.
Try's asking, is this good to help us determine patterns before we use MassQL? So I'll venture this one just, Amy, but I think so. Imagine that this is one of the inspirations that originally came to our minds when we started this, is revealing the patterns of fragmentation all at once. Just historically, a lot of people have been visualizing spectra and molecular networks one spectrum at a time, or at best, pairs of spectra in these mirror plots. But in these families, you could end up with tens to 100 MSMS easily, right? And so if we visualize this all at once, we can see the peak sets that are moving in mass or being stable in mass, or perhaps they're moving in mass, but they actually have a consistent neutral loss or something like that. And so given that visualization, you can, of course, run statistics and ask that question. We built tools like that. But we feel like that this visualization gives you some intuition as a mass spectrometrist on what is actually consistent and when is it consistent enough to be useful to you. And then paired along with the information, if you might have some insight from the libraries or in silico, or you just know the molecules, their inherent, their actual structure, so you can kind of figure out, okay, you can start designing these MassQL patterns that you can go back now and start creating the query and start searching more data. So that's one way that I think would be cool. But again, if you have the idea, try it. I think we have finite creativity, but you all actually do real stuff. So let us know what you think. So I think that's one of the greatest strengths of a platform like this, right? So.
Oh, I had a question actually. I think this was from your slides, when you were showing how it maybe picked like a blue peak instead of a green. I think it was the slide before this. Oh yeah, the limitations. Yeah. Yeah, so it picked like that blue peak instead of the green peak. I am wondering if you could talk about like maybe why that happens with this algorithm. Maybe I won't understand it because I'm not a data scientist, but yeah, just kind of curious like why you get these false picked peaks maybe.
Yeah, thank you for asking. So basically our algorithm scores, okay, so step back. We have pairwise cosine similarities at first, and based on those pair sine cosine similarities, the algorithm also computes all possible peak matches between, let's say, two spectrum. And then, given those peak matches, we start to create peak sets. And when we're doing that, we have to consider shifted peaks and exact match peaks. So in this case, our algorithm chose to include these ones because it increased the alignment score, so that cosine similarity score, versus this one, which is, I think because you can see it's like slightly less intensity versus, this one. And also our algorithm tries to maximize the size of the set as well. So we would include these, but the algorithm chooses to include this one versus the green one, because now we have a set of size 7, including this bottom blue one versus just 5.
So
Yeah.
is there a way to kind of find those false positives or improve it? Or is that up to chemists to be like, oh, that mass delta doesn't make sense? Must be
It
wrong.
is, as far as I know, it is up to chemists, and we realized that because they were manually computed or manually looked at and compared with our algorithm output, and we're like, oh, this isn't right.
Okay, thank you.
Right. And so just to put a bow in kind of Amy's explanation, it's a limitation of this greedy algorithm that we chose. And okay, so again, don't shoot me, but like my analogy for this is when you try to find this alignment across all the spectra, it's hard for us to think about that big problem as computer scientists. So we start breaking it down and we want to make the algorithm fast. So we do all these small pairwise alignments that lock it in. So it's kind of like growing a crystal. But if you like screw up at the first step of growing the crystal, it's going to look bad, right? And so we lock in potential errors at the very small point, and then they stay with us whenever we have the full alignment. That's a limitation of this greedy method. But the benefits of this greedy method are it's very simple to implement and it's very fast for larger sets of spectra. But from a computer science perspective, And given our way of defining the problem, it can give us these weird suboptimal results that Amy's pointing out.
I mean, great presentation, Amy. Just to stop you, I think you were talking about the USI Playground GNPS2 website to get all these USI index. Just wanted to let people know that in the Bang Bioinformatics Lab, there are a bunch of tools in Tool Index. Sometimes I use them, but not many people know about that. So I just wanted to share the link here. I recently used this as well to get the USI index. So
yeah, I just put it in the chat. Thanks,
okay.
Thanks, Absur. Yeah,
Yeah,
I don't
sure.
even remember all these things. At least somebody's looking at the tool index, so I'm glad that it's useful.
Yeah.
And okay, so here's another question. Can this tool be used to find common peaks in large data sets for over 1,000 samples and exports, top end common peaks within a data set? What do you
Okay,
think,
so
Amy?
size-based, I don't think I've tested with over 100, but I know it works up to around 100. Hold on, let me look at the rest of the question. We currently don't have a feature for exporting a CSV with the top and common peaks in a data set, but maybe we can think about putting that in the future.
No, that sounds great. I think it should scale, number one, just as a feedback, because if we're talking about molecular networking, we can just run this on every component, and then you output kind of a summarized set that's put together. But anyway, we'll have to cross that bridge when we get to it. But yeah, I think that's doable. Okay, here's another question about the limitations. What happens if you permute spectrum 1 and 2? I presume swapping the order and things like that. In this particular example, will all the peaks align at 351.08? The one that, the red with the red peaks, kind of the problem you pointed out, Amy. What do you think?
We saw this one and this one.
Yeah, if the order in which you actually build up the greedy alignments, I think that's the spirit of the question.
That it might. So the thing about this approach is that the order that we process the spectra in affects the entire output and alignment. So when we're doing it pairwise, it would be this one and then this one and then this one. So yes, if we switch 1 and 2, I think it's pretty likely that the algorithm will choose to keep this peak instead, but I have not tested that out yet, so I can't say for sure.
Yeah. And one other thing I think that was a little glossed over is we decide the order as part of the algorithm. So what we do is we define a maximum spanning tree, and then that's our ordering in which to do the greedy alignments. Now, it's deterministic based upon the input from the molecular networking. And we could change that algorithm, but the problem with these greedy algorithms is you kind of fix one thing in one spot, and then you cause a problem somewhere over there. So it's a game of whack-a-mole for the Americans out there, but so it's probably not as simple as just simply swapping it. For us as computer scientists, we want to think more globally. Is there like a global optimization that can optimize exactly what we want to look for? So that's a separate point. That's a separate thing that we could do. Okay, so here's a question from Paolo. Do you think this would be a good approach to check and choose the nodes I can collapse for further statistical analysis using feature-based molecular networking? I'll feel this one, Amy. Maybe there's some sort of keystone fragmentation molecules. Maybe that's a way that you can prioritize it. But a lot of what people do in at least metabolomics is kind of the statistics first, right? Rather than looking at identification first. But you obviously could. we always thought it would be more useful to make sense from a structural elucidation perspective of if you could see this global alignment. For one example, if you see this global alignment or this multiple alignment, and you can identify one molecule in there, right? And you can enumerate the fragmentation and all that stuff. Before, you would have to do like a pairwise propagation across the network to identify one more, another. Here, we always thought that, well, you have this full alignment across everything. You can basically do a site localization of all the modification across the entire network all at once. So that's kind of how we were thinking about it. But again, if you want to do the combine with statistics based upon what things were accessible for being identified, maybe that's a decent approach as well.
Can I ask another practical question? So like thinking of multiple alignments, of course, like sequence alignments is the first thing which comes to my mind. Is there a straightforward way to construct now a tree out of your alignment?
So that's a good question. We thought about this originally, and we did not. There is technically a tree in the background. Now, with the multiple sequence alignments, they have a kind of a hierarchical tree. We don't impose a hierarchy on the tree because there's a specific semantic meaning when you're talking about sequences and evolutionary distance. Here, we don't particularly have that notion. Of course, we can. And this borrows from some ideas from the Met family work by Stefan Neumann's group. But we haven't thought too deeply about it. Rather, we were thinking about, when you look at the multiple sequence alignment from protein sequences or DNA sequences, you see the amino acid deletions, insertions, polymorphisms, and they have this color scheme, right? So we wanted to bring that idea for the mass spec, that one part. Now you're asking about the tree on the other side. Of course, we can provide the tree. It wouldn't be significantly different than a molecular network, at least right now, just because we don't have a good framework to think about what do the distances mean. But that's not to say we shouldn't think about that.
I mean, I think a key difference to the molecular network and the modified cosine would be that you're not limited to one modification.
Right, but the molecular networking already affords you that because they could be, you don't have to have a direct connection, right? They could be several hops away. And we want to think about taking advantage of multiple hops. Then I think the piece of work that we should think more about or bring into the conversation is the transitive alignment paper we published a few months ago. So I think that solves one of these problems. But again, it's this question about what does that distance actually mean?
Cool.
Okay, any final questions and thoughts? Well, check it out. It's all available, as Amy said. And well, let's give Amy a round of applause. That was a great job. Especially, I think, just to point out, this is our first undergraduate in the VMOL seminar. So if you have other really talented undergrads doing great work, reach out and have them present. As maybe, Amy, you're holding them to too high of a standard, but at least I thought it was great. And thank you all. And yeah, be on the lookout for some manuscript coming out.